Hey, Grade 10s. As promised yesterday, we just quickly introduced to you the idea of, or reintroduced, I guess, naming and writing the chemical formulas for ionic compounds. And I said to you that basically what we did yesterday was a review of what we covered in Science 9, and hopefully your work on the worksheet over the last few minutes was enough to get you moving forward on that, and you've got some ideas. What I want to do now is throw you two new things that we did not look at last year. Now these aren't super complicated, but what they do is they just add another dimension to our understanding of ionic compounds and the kinds of things that are out there. Um, and it's going to have us looking a little bit more deeply into um, two particular um, curveballs that I'm going to throw at you, but like I said, give you a deeper understanding. So the first one is ionic compounds with multivalent atoms. So you'll notice that on the periodic table, some atoms have more than one stable ion. So these are known as multivalent elements. I'm going to drag a screen in here and show you what I'm talking about. So this is your periodic table that you guys have been using, and what you can see is once we start to get into the fourth period, the fifth period, the sixth period, you're going to notice that there's some of these chemicals in here like vanadium and chromium and titanium, niobium. We've even got, there's not very many over here, cobalt and iron. And then if you went over to the next page, you would see some more on here. So these are what we call multivalent metals. And when we're coming up with IUPAC names or chemical formulas, it's important for us to be able to understand how to work with these and communicate them properly. Okay. In other words, another way to look at this is we need to be able to find a way or understand which version of platinum we're using. Are we using the version that is a 4 positive, or are we using the version that is a 2 positive? Which version of gold are we using, 3 plus or 1 plus? And so there's ways that we communicate this in both our chemical formulas and in our IUPAC names. So first things first, to come up with the name for one of these. So I've given you two examples here of two different element or two different compounds here. What we have to do first, and I'm trying to click on my pen here to get it going. What we have to do is we have to try to determine what's making up these. So we know we have a chromium, but if you check on your periodic table, chromium has two versions, a 2 plus and a 3 plus version. So I'll just drag this back in here just to show you. So it's got a 3 plus and a 2 plus version. So what are we actually using? Which version of chromium are we using? In order to figure that out, you actually look to the nonmetal first. So in this chromium sulfide, we have 3 sulfur ions. So 3 sulfur ions is S2 minus, S2 minus, and S2 minus, which gives us a total of 6 minuses, right? 6 negatives. We know in ionic compounds that then our negatives have to be canceled out by our positives. But what's important here is we only have 2 chromiums to work with. Now, as we saw, there's 2 versions of chromium. There's a 3 plus and a 2 plus. If we were working with the 2 plus version and we only had 2 chromiums, so Cr2 plus and Cr2 plus, those two would only come to a total of 4 plus. And that's not enough to cancel out the 6 minus. So we cannot be using chromium 2 plus. We must be using chromium 3 plus. So if I have one 3 plus and a second one, that is going to give me a total of 6 positives, which cancel out my 6 negatives. So when I write down the name, and I don't know if there's an easy way. So in order to communicate that we have the 3 plus version of chromium, we're going to start to use Roman numerals in our names to do that. I'm hoping that you remember your Roman numerals from math, but if you don't, Roman numeral 1 is this, and that represents 1. This is 2. this is 3, this is 4, this is 5, 6, and then I'll go up to 7 because I don't believe there's anything more that you guys are going to need to do past 7. Okay, so those are your Roman numerals from 1 to 7. Now we're dealing with chromium-3. And so what we would write out, and this is going to look terrible because I can't figure out how to type using this. So we're going to write out chromium. I look like I'm a 5-year-old writing, but that's fine. And then you're going to put in brackets, or sorry, in parentheses, a Roman numeral 3 to indicate that we're dealing with chromium-3. Now, if we were dealing with chromium-2, we would use a Roman numeral 2, but we're not in this case. And then we would put sulfide at the end. So SUF or SULFIDE, and we're done. Okay? So it's my horrible writing. That is chromium, Roman numeral 3, sulfide. Now, the same will be true here for our iron bromide of some sort. We would have to go and look at bromine. We would know that bromine is a 1- ion, but we have 2 of them. So that gives us a total of 2 minuses. So each bromine is 1 minus for a total of 2 minuses. And we only have 1 iron that we can use to cancel that out. So going back to our periodic table and finding iron on here, we have a 3+ version and a 2+ version. We only have one of them to work with. So the easy one, or the one that we would have to choose, is the 2+ version. And so we would have to communicate that on here by calling this iron. So IRON, and then parentheses with the Roman numeral 2 for 2+, and then bromide in there for our name. Okay. Now, if you need to go from a chemical formula into the IUPAC name, so the opposite of what you're doing, you'll be given this name, and you'll have to pay attention to the Roman numeral to tell you what charge your metal is. Now, before we leave this and we move on to the polyatomic ions, just to remind you that the only time you will use Roman numerals is when your metal is multivalent. So when you're using something like titanium or vanadium or chromium or manganese or iron. All of these ones over here and elsewhere that only have one version of the ion are not multivalent. You do not use Roman numerals for them. There's no need to use them because we don't need to communicate that there's a different version. So it will still be potassium chloride, no Roman numeral. But when we have something that is multivalent, like many of these ones in here, and further on onto this page, you're going to need to use those Roman numerals, but only when it is multivalent. So I hope that makes sense. I'm going to scroll back up here because we're going to need that in a second. Now, the next thing that we're going to talk about is polyatomic ions. Now, the word polyatomic is pretty simple to understand. The prefix here, the prefix poly, means many, and atomic. So these are ions that are made up of many atoms. So everything we've been dealing with so far would be what we'd call monoatomic ions. It would only be one atom making up that ion. So it'd be something as simple as copper 2 oxide. That's one atom and one atom. And so this is an ion and this is an ion. We have polyatomic ions which are made up of more than one atom. So for example, I'm going to put my laser pointer so you guys can see better. These are made up of non-metallic atoms. So for example, something like phosphate, which is PO4 and with a 3 negative charge. So this is made up of many atoms. It's made up of 1 phosphorus and then 4 oxygen atoms. Now, polyatomic ions you don't just have to come up with out of nowhere. There is a table of polyatomic ions above your periodic table. And so this is the table of common polyatomic ions that you guys will be working with in this class and future chemistry classes. And so you can see, for example, that phosphate is up here along the top. And we have other sorts of polyatomic ions here. I'm just going to make this a little bit bigger. What's important to note about these is they all have an ion charge associated with them. So you're going to treat them just like any other ion, any other non-metal ion. The only other one I want to highlight on here, and I'll actually physically highlight it, is ammonium. Oh, I highlighted everything. Good job. Okay. Ammonium is right here. Now, ammonium is the only positively charged polyatomic ion. Everything else on here, if you scroll through, is negative. So ammonium behaves like a metal. All of the rest of these, we're going to pretend that they behave like nonmetals. So they become the second part of the name or chemical formula that we're talking about. So to name a compound containing a polyatomic ion, simply name the cation first, as we've always done, and then the anion. What's different here is that there is no need for us to change the ending of the polyatomic ion's name. So if your polyatomic ion is phosphate, you just leave it as phosphate in the name. No need to change it to an IDE or anything like that. When you're writing the chemical formula for these compounds, you use the same rules as we did for the other ones. The only thing that's different is it may be necessary to use parentheses or brackets if you have to use a subscript to tell me how many of the sulfates you might be using. So we use these parentheses here to tell us that, I'm going to get my pen out again, to tell us that there are 3 of what's inside the parentheses, though there are 3 sulfates in this case. So I'm going to do a couple of examples and we'll work our way through these. And then again, if these aren't making sense, when I'm back tomorrow, we can sort this out. So calcium and this thing right here, OH, inside of a bracket, that's usually a pretty good clue that you've got a polyatomic. So this isn't calcium, oxygen, hydrogen. This thing actually has a name. And if we go to our table of polyatomics, we'll see that OH is right here. So its name is hydroxide. Okay, so we're going to treat this then as this is our metal, and we would write its normal name as calcium. Okay, and then here is our non-metal, but it's actually a polyatomic, and we just write down whatever the name of the polyatomic is inside our data booklet above our periodic table. So this is calcium hydroxide. Pretty simple. Sodium phosphate. So whenever you see an ATE at the end of a name in a chemical formula, in an IUPAC name, that's usually an indication that you're dealing with a polyatomic. So phosphate, we already found, is up here, okay? And we know it has a 3- charge. So we've got sodium that has a 1+ charge, phosphate, which is PO4, and it has a 3- charge. So sodium, one sodium to the party, and a phosphate to the party. The sodiums aren't able to cancel out the phosphates. So we would add another sodium. That gives us 2 pluses. That still doesn't cancel out the 3 minuses. So we'd add a third sodium. Now we have 1, 2, 3 pluses, which will cancel out our 3 minuses. And so we would write this simply as Na and then PO4. Oh, and I forgot that there are 3 sodiums. I don't need parentheses around the phosphate because there's only one of them. If there's more than one of them, like there is up here or there is here, then you need those parentheses. This next one here is made up of ammonium, which is pretending to be a metal. It's our only positively charged polyatomic ion, and then another polyatomic ion, SO4. So this is not ammonium, sulfur, oxygen. SO4 is actually also a polyatomic as well. Here it is right there, sulfate, and it's a 2- charge, which makes sense because our ammonium is a 1+ charge, and we have two of them. So two 1+s gives us 2+, and a 2-, those cancel each other out. So this is simply named ammonium sulfate. I'm not going to write it out because it's tedious to do that. Then this last one, ammonium hydrogen carbonate. There's ammonium again, and we know that ammonium is NH4, and it's 1+. Hydrogen carbonate, that's a really long thing. Can you find hydrogen carbonate on the periodic table? Nope. But you can find hydrogen carbonate in here. And there it is right there. And it is HCO3 with a 1- charge. So this is going to be HCO3 with a 1- charge. And so I bring one ammonium to the party and one hydrogen carbonate to the party, and we end up with NH4HCO3. Because there's one of each of them, we don't need to put parentheses around each of them. All right, so that is what you need to know for multivalent and polyatomics. As always, if this doesn't make sense right off the bat, please don't get frustrated. I'll be back tomorrow. We can work your way through it. Your sub will do a good job of explaining this too, I know. So work your way through as much of this as you can. And if you've got any questions again tomorrow, we'll wrap them up. Best of luck, and we'll see you.